Hello everyone. Let us try to understand the process of equalization, and we will see that how the equalizers will be used in a baseband transmission system to cancel out the effects of intersymbol interference. Let us look at the system model first. This particular these are the input bits which will be going into the system after modulating onto a pulse. Let's say we choose GT as the pulse. So that means these bits will be modulated onto GT pulse. The choice of the GT pulse will be in the hands of the designer, and we know that if we use the raised cosine pulses, then we shall be able to achieve the uh, fulfill the Nyquist criteria for zero ISI. And these modulated pulses will be passed through the channel. The channel impulse response is given by CT. After going through the channel, the noise will be added into the signal. So ZT is, let's say, the noise added into the signal that is passed through the channel. At the receiver, the signals will be received through a receiver filter. In the receiver filter can be a match filter, which is an optimum filter because it maximizes the signal to noise ratio. We all know that. After the signal passes through the match filter, which is basically a receiver filter, the signal will be sampled, and after every capital T seconds, then the signal will be detected and the decision will be made in favor of whether a 1 was transmitted or a 0 was transmitted in the case of a PAM system, to in the case of a binary PAM system, or if it is some other modulation criteria is used here, then accordingly the decision will be made. Now, HT, what is HT? HT is the combined response of the pulse and the channel impulse response. XT is the combined response of HT and MT. That means GT. XT is basically the transmit pulse, which is GT, the convolution of the channel impulse response, which is CT, and along with the convolution of the receiver filter response, which is MT. So that means XT is basically GT convolved with CT convolved with MT, right? So that means at this point, before this sampler, YT signal will be received, which is basically the input pulses, and the delayed, we can say that it is the delayed version of the XT pulses received here, right? XT minus NT. It's actually a bit stream of pulses. So bit stream of pulses modulated with the I mean the input bits, right? So these pulses, that's YT is actually the overall waveform that we will receive. The input bits will be modulated onto the pulse, passed through the channel, received at the receiver. XT is the convolution of GT, CT, and MT, and IN bits are modulated onto the waveform. So ultimately we receive this signal, uh, summation of this term IN x Tn minus T as YT here, and plus noise will also be will also occur at the receiver after the receiver filter. Then the signal is sampled after every capital T seconds, and after the sampler we will get YK, which is the sampled version of YT, and from this term we will separate out the term when n is not equal to k, that means the present symbol, right? We will, for doing the sampling, what we will do is we will put t equal to k capital T. So once we do K capital T, then if we extract one term out of this overall term, which is n equal to K. So when n is equal to K, this K capital T minus n capital T will become 0. So that means it will be x0, right? We can take it out and we will put it equal to unity. So once that term is put equal to unity, for n is equal to K, Ik will be separately put out here, and all other terms n going from 0 to infinity but n not equal to K will remain here, and plus Vk, the sampled version of the noise. Actually, this is the ISI that will be introduced into the system. The effect of the previous bits onto the present bit, the spilling over effect of the previous bits onto the present bit. So that's the sampled signal we get here after the sampler, and then the decision has to be made. Now the problem at hand is to remove this ISI. We know that the if we select the raised cosine pulses, we will be able to get the uh, Nyquist criteria for 0 ISI satisfied, and we can make this term as 0. But that is only in the case when the channel is constant. That means channel is not varying. But in all practical cases, channel is random, channel is time varying. So if the channel is varying, we cannot adaptively change the pulse every time. Change the shape of the pulse every time, depending on the conditions of the channel, uh, right? Because the channel actually is time varying. So in that case, some it will not be practically feasible that the complete ISI will be removed. The ISI will still remain there even if we have tried to fulfill the criteria of tried to fulfill the Nyquist criteria of 0 ISI. In that case, we will have to do something before the detection, right, to cancel out the effect of intersymbol interference, and that job is done basically by the equalizer. And that process of mitigating the effects of the intersymbol interference will be called as the equalization. Right, let's look at the details in coming slides. Now, transmitter sends discrete time symbols at a rate of 1 by t capital 1 by t symbols per second, and the sampled output of the mesh filter at the receiver is also a discrete time signal with samples. So we have already seen that. Now the cascade of the transmit filter at the input channel with impulse response GT, the channel. So all these things I have already explained. And this is the sampled version of the signal that we get after the sampler. Right. This is the equivalent discrete model of this equation only, because for all modeling purposes, we will say that it is a discrete time model of the channel with ISI. Now, to process this signal further and to introduce the concept of equalization, let me have the presenter view here. It is desirable to whiten the noise sequence by further filtering the sequence YK. So we will actually pass it through a whitening filter. Now, what is whitening filter? The noise usually has non-flat amplitude spectrum. It's not flat. The noise whitening module equalizes the spectrum of the signal, making it similar to the white noise spectrum. Right? Noise whitening module works similarly to the automatic filter that enhances low-level spectral components and attenuates high-level ones, because it will bring all the frequencies to one particular almost the constant level, like the white noise level. And after that, additionally, de-emphasis is applied after whitening where high frequencies are attenuated so that spectrum of the processed signal is similar to the spectrum of the speech signal. That is in the case of speech signal. We can do the de-emphasis also. Whitening and de-emphasis enhance the quality of the speech signal. This module is especially useful if constant whistling is present in the recording. So since we are here at present talking about a very general case, not about the speech signal, so that means our signal has to pass through a whitening filter which will give it a white or a flat spectrum like white noise. So this is accomplished by passing YK sequence through a noise whitening filter with response 1 over f of 1 by z. The output sequence Vk can then be expressed as, because Fn is the whitening sequence and Ik. So this is how our output sequence will look like after passing it through the whitening filter, where eta k is a white Gaussian noise sequence and Fk is a set of tap coefficients of a digital filter Fz, representing the cascading of transmitting filter, channel, match filter, sampler, and noise whitening filter. So that means we have passed through these stages: transmitting filter, channel, match filter, sampler, and then noise whitening. From this we can, so this is the discrete time model of the channel with AWGN, which is white Gaussian noise. All right. Now we will talk about, after the whitening filter, now we will talk about what the equalizer is. Now we are actually discussing the requirements and the system that will represent the equalizer. The linear filter most often used as equalizer is linear transversal filter. So its input sequence. So we will apply this sequence as input to the transversal filter, which will be an equalizer. We will see further the conditions of what are the other conditions of equalizer. But this is the input sequence that will be applied to this transversal filter, linear transversal filter. Its output sequence is the estimate of the, now after the equalizer, actually what was transmitted, if you look at the, so this was the this in was the input sequence, input bits that we transmitted, and we have to actually estimate the at the equalizer output what are these bits which were actually transmitted. So we will get an estimate after the sequence is passed through the equalizer. Then we will say Ik hat is the estimate of the information sequence, right? And which is the estimate of the whatever was transmitted as ones and zeros, and we will pass it. Basically, equalizer is a filter with Cj representing the response of the Cj representing the coefficients of the filter. It will be a 2k plus 1 the tap weight, because j will vary from minus k to k, including 0 of the value of j can be 0 also. So number of coefficients or number of taps in this filter will be 2k plus 1. So basically it is the convolution of the Vk sequence, which is input to the equalizer, and the filter coefficients, which acts as basically as an equalizer. And that's the, after convolving with the, after convolution of the input sequence and the filter coefficients, equalizer filter coefficients, we will get the estimate of the estimate of the sequences that we transmitted. Now if Ik hat is not identical to the transmitted information symbol Ik, then of course that will so therefore the error will occur. We will have to design system so that Ik hat will be as close as possible to the original transmitted sequence. Now if it is not, then the error will occur, right? And we will have to design the equalizer based on certain criteria, right? Let's look at those criteria also. This is the representation of the transversal filter. This is the delay line, right? These are the coefficients of the filter. pass through the, so there will be some algorithm for tap adjustment. We will see the criteria, what criteria will be using for the selection of the coefficient, and finally the output will be at the output, the finally will be the output, which is the equalized version of the final output. I mean, you will get ik hat here. Fine. Now let us look at the algorithm which we will use, or the criteria that we will use to optimize the coefficients of the equalizer. Now, two main criteria which are used for the purpose of optimizing the equalizer coefficients. First criteria is peak distortion criteria, and the second criteria is minimum mean square error criteria. Okay, now let us look at the peak distortion criteria. The peak distortion criteria deals with the worst case intersymbol interference, and which is given by the transmitted symbol minus the the expected output of the symbol value. So this absolute error must be minimized. So this is known as peak distortion criteria, that the minimization of this performance criteria. What is the performance criteria? That the error value, which is the difference between ik minus ik hat, this has to be minimized, and this is known as peak distortion criteria. Now, the output of the whiting filter, right, cascade of the cascade of the whiting filter and the equalizer. That means Fn is the response of the whiting filter, whereas the equalizer response is given by Cn. These represent the coefficient values. So there is a convolution between the output of the whiting filter and the equalizer response, and this value is given by Qn equal to sigma j going from minus infinity to infinity Cj Fn minus j. Now we can express this term. We can extract the term corresponding to the present symbol, which will be our Q0ik. We have already done this exercise of extracting the present symbol value, scaled value of the present symbol, and the ISI. And similar thing we are doing here, that the expected value of ik is given by the present symbol, present, which is the symbol in question that we are trying to detect. Q0 is only the scaling value, the scale, that's why it is called as the scaled symbol. Now this value represents the ISI, the effect of the previous symbol, and this is the noise value after going through the whiting filter, so we are taking it as AWGN noise. Now the peak value is given by, the peak value of the ISI is given by sigma n going from minus infinity to infinity, n not equal to 0, modulus of Qn. So we can express this term like this, right? Now intersymbol interference can be eliminated by making this value, this term as 0. So in that case, that is Qn equal to 0 for all n except n equal to 0. So that is the time domain criteria for eliminating the intersymbol interference completely by the peak distortion criteria. Now if we take the Z transform and solve this equation, we will get Qz equal to Cz into Fz. Right. Now what is Cz? Cz is the equalizer response, Fz is the channel response. So Cz is the reciprocal of the channel response. That means whatever the channel has done with the signal, whatever is the channel response, so if we invert that response in the equalizer, so all the ISI present, all the distortion present in the signal will be eliminated. That's what is peak distortion criteria. Intuitive, but please remember that peak distortion criteria is in the absence of noise. We are not considering any noise value in this expression, in the expression of Qz, while we are putting it while we are putting a condition for 0 ISI, we are not considering any noise term here. No noise term has come in Q set also, and similarly the equalizer response also, there is no noise term. That means it is in the absence of noise. The peak distortion criteria is in the absence of noise. Intuitively, it seems to be a good choice as it inverts the channel response. That's very true, because whatever the channel response is, we just invert the channel response, so we will be free of all the ISI present in the signal. This criteria leads to zero ISI. Hence, this type of equalizer is also called zero forcing equalizer, because it makes ISI go to zero. But there is a drawback of this peak distortion criteria or zero forcing equalizer, because, for example, if the signal is passing through the channel, in some bands of the channel, the channel response can be very bad. That means there is a lot of attenuation in some bands. Now, if the attenuation levels are very high in certain bands, and we have selected an equalizer which just does the inversion of the channel response. So wherever the channel response is very bad, so the inversion of that thing will be complete amplification. So in that case, the noise will also be amplified. So that's what is the drawback of zero forcing equalizer, which says that it amplifies noise in some bands wherever the channel has high attenuation. Therefore, we can say that this technique amplifies noise. The transfer function of the equalizer Cz is simply the reciprocal of Fz. So that's the same thing put in the diagrammatic form, which is zero forcing equalizer. Cz is just Fz, and we are getting the expected value of the symbol, free of ISI, but the drawback is that it will amplify the noise also. Okay, the second criteria is mean square error criteria. Mean square error criteria says that the error value is ik minus ik hat. We know that. And what we will do, we will take the expected value of the square of the error. So where ik is the information symbol transmitted in the kth signaling interval, and ik hat is the estimate of that symbol at the output of the equalizer. That's very clear. That's ik is the symbol transmitted, ik hat is the estimate of the symbol that we are trying to make. The performance index for the mean square error criteria denoted by J is the expected value of the square of this error, right? So expected value of ik minus ik hat square. Now, if we solve this with this criteria, if we try to solve for the response of the equalizer, we will not go into the details of the solution, but I will directly put the solution here. And important thing is that mean square criteria takes into account the noise factor and not. Whereas in the zero forcing equalizer, it was all in the absence of noise. But here we take the noise into consideration. The equalizer filter response we get in this criteria can be derived to be Cz equal to 1 over Xz plus N naught. So what is the meaning of this? This N naught is the power spectral density of noise. It is when N naught is very negligible, so it will be equivalent to zero forcing the equalizer only. But it takes into account the noise value also. So therefore, the noise amplification will not take place in mean square error criteria, minimum mean square error criteria, which was a drawback in the zero forcing equalizer. So that drawback is overcome with this criteria, minimum mean square criteria. Now let us look at the role of the equalizer in general, and then we will talk about the decision feedback equalizer. So these are the constellation points at the transmitter side. So transmitted sequence, one of the constellation point will be transmitted through the channel. Depending on the input symbols, one of the signals represented by one of the constellation points will be transmitted through the channel. The noise will be added the noise will be added while moving through the channel, and we put an equalizer here. Now what is the job of the equalizer? When we receive this diagram corresponds to the received symbols, now without passing through the equalizer. So when we pass the signal through the equalizer, the points are very well placed. Right now here we can make a decision about the present. We can make an estimate of the present symbol, that to which constellation point it belongs, because we will use the nearest neighborhood approach, and we will detect, basically make a decision. Okay, this symbol was transmitted from the transmitter end. This is in general, you can say, the description of the application of the equalizer. An equalizer is a digital filter that is used to mitigate the effects of intersymbol interference that is introduced by a time dispersive channel. Now let us look at the decision feedback equalizer. Decision feedback equalization makes use of previous decisions in attempting to estimate the current symbol. Right. So let us look at the block diagram of the decision feedback equalizer. Now input, this is the VK is the input coming from the mesh filter. This is a feed forward transversal filter with K1 plus 1, K1, K subscript 1 plus 1 taps, right? So these, from the output of this filter will go to the symbol by symbol detector, and the decision is made that what symbol is transmitted. Now let us say that, let's say the first symbol comes here, right? First symbol comes here, it contains some information about the channel. So what we will do is, the information present in the received symbols will be fed back to the uh, will be fed back, and this information which is fed back will help in the detection process of the where this symbol by symbol detection will take place. I mean, that's what is said here. Decision feedback equalization makes use of previous decisions in attempting to estimate the current symbol. That's what is being done here. So previous decision will be made here. So that decision will be fed back through this feedback filter, and this feedback process will help in making decision of the future symbols. So that is basically the idea of decision feedback equalization. Any trailing intersymbol interference caused by previous symbols is reconstructed and then subtracted. The DFE is inherently a nonlinear receiver. However, it can be analyzed using linear techniques if one assumes all previous decisions are correct. The feedback filter accepts as input the decision from the previous symbol period, thus the name decision feedback. Feed forward filter will try to shape the channel, so rest of the things remain the same. A DFE is a non-linear equalizer. So that's just the explanation of the decision feedback equalization process. That's the basic idea of a decision feedback equalizer. One of the important 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 I mean the condition, but one of the important advantages of the decision feedback equalizer will be that it will reduce the complexity of the feed forward transversal filter, because this feedback filter is actually helping us to make decisions based on the previous decisions, and certainly the load on the feed forward transversal filter will also reduce, and load in terms of the number of tabs and the complexity of this filter, and overall decision feedback filter will be estimating the symbols based on these two filters. One is the feed forward filter and the other one is the feedback filter. All right. Now, equalizer output can be expressed as ik hat, where j goes from minus k1 to 0, cj vk minus j equal to 1 k2, cj ik hat minus j, where ik hat is the estimate of the kth information symbol, cj are tab coefficients of the filter. All right. So this term corresponds to the feed forward filter. This term corresponds to the feedback filter. All right. So that's the idea of decision feedback equalization. Now the coefficients of the feedback filter are given in terms of the coefficient of the feed forward section by the following expression. These are the we can derive the coefficients in terms of the feed forward filter also. The DFE determines the ISI from the previously detected symbol and subtracts it from the incoming symbol. The equalizer does not suffer from noise enhancement because it estimates the channel rather than inverting it. It actually estimates the channel based on the filter characteristics, and it does not invert the channel as we were doing in the case of uh, zero forcing equalizer in the absence of noise, and to some extent in the case of mean square error in the presence of noise. The DFE has better performance than the linear equalizer in a frequency selective fading channel. The DFE is subject to error propagation if decisions are made incorrectly. Now let's look at one more type of equalizer, that will be fractionally spaced equalizer. But all these equalizers we have discussed till now, these are symbol spaced equalizer. Conventional equalizers have tap spacings that are spaced with respect to the symbol rate. Whatever is the symbol rate, the tap spacing of the filters is basically equal to the symbol rate. I mean, the with respect to the symbol rate. Now, it is known that an optimum receiver corrupted by Gaussian noise would have a matched filter sampled periodically at the symbol rate of the message, and that the matched filter must be matched to the channel and corrupted signal prior to the. Okay. Now, since the channel response is usually unknown, the optimum match filter must be adaptively estimated. A suboptimal result would cause degradation in performance and sensitivity to timing error from the sampling of the output. Now, let us understand what is the principle behind the fractionally spaced equalizer. Uh, Fractionally spaced equalizer is based on sampling the incoming signal at least as fast as the Nyquist rate. Fractionally spaced equalizers have taps that are spaced closer than the conventional adaptive equalizers, and with a sufficient number of taps, it is almost independent of the channel delay distortion. And these are the if the transmitted signal consists of pulses having a raised cosine spectrum with a roll of factor beta, then this signal spectrum extends up to, that's the width of the signal spectrum. It will be 1 plus beta divided by sampling time. And what about the sampling rate? The sampling rate must be at least 1 plus beta divided by twice ts. So that's the equation that you will have to use for the fractionally spaced equalizers. Now that's actually the block diagram of the fractionally spaced equalizer with a tap spacing of m by l TB. That's the bit time. So uh, now this is the input signal, and this is S of cap n hat S hat n is the output signal. Now the signal is upsampled by a factor of m throughout, and ultimately it will be downsampled by a factor of l. So that means in a way these taps are spaced fractionally with a fractional ratio of m by l to the sampling rate, to the sampling time. All right. Now let us look at what are the advantages and disadvantages of a fractionally spaced equalizer as compared to the symbol spaced equalizer. A fractionally spaced equalizer has the following advantages over its symbol spaced counterpart. It has got no sensitivity to timing phase, superior performance in most of the cases. Symbol spaced equalizers, on the other hand, may offer lower complexity in some cases, but that's not always true, right? But the performance of the fractionally spaced equalizer will be better as compared to the symbol spaced equalizer. So the important point is that The spacing between the taps is fractionally achieved through the process of first interpolating the signal, and then first interpolating the signal, then passing through the channel, and at the receiver you will have to downsample. So that's basically, after the equalizer you will have to downsample the signal. So that's basically the principle of fractionally spaced equalizer. I finish my lecture about the equalization here. Thank you. The equalizer that